So solution concentrations. We know that when we put table salt into water and stir it up, it seems to disappear, right? But it's still there, because if you taste the water, it's salty. And if you were to take that water and boil all the liquid water away, the salt would be left behind. The table salt and the water make a homogeneous mixture, and in chemistry we call those solutions. A solution has two parts, a solvent and the other stuff. So the solvent is generally the part of the mixture that is present in greater amount. It can also be described as the part of the solution that keeps its state. So in this example, table salt is a solid, and when it goes into the mixture is a liquid, and so the table salt has changed its state. The liquid water is still a liquid as the solution, and so it has not changed its state. The solute is the other part of the solution. That's the part that's present in lesser amount. The solute may or may not change its state. There can be more than one solute. So to that salt water you could add sugar, and then you'd have two solutes, but there's always one solvent. The composition of a mixture can vary, and so when we talk about solutions, we need to describe how much of each component is present. We can't just use a single word, such as salt water. Well, I guess that would be two words, but we have to describe the relative amounts. We can do this qualitatively using the words dilute and concentrated, and these mean the same thing they do in everyday life. A dilute solution is going to have a smaller amount of solute, and a concentrated solution is going to have a larger amount of solute. So this always makes me think of frozen orange juice. You can buy little cans of frozen orange juice concentrate at the grocery store, right? Do you want to thaw that out and drink it straight out of the can? No, it's going to be really sweet and thick, right? Because it's concentrated. They took a bunch of the water out. So what you do is you put the can of orange juice concentrate into a big pitcher and you add some water to it. You dilute it, right? You make a more dilute solution. So that's the same way we use the words dilute and concentrated in chemistry. So one of the most common ways to express the concentration of a solution in chemistry is the unit molarity. Molarity is abbreviated with a capital M. It is the amount of solute in moles divided by the volume of the solution in liters. And this is something we need to know about to do the calculations in today's lab, right? You should have seen this in your prereq for this class. So it's the amount of solute. So in our example with the salt water, it would be the mass of the salt water converted into moles, right? Divided by the volume of the whole solution. That makes sense? So here's an illustration of how to make a specific concentration. I lectured on this yesterday and did the same experiment with my class yesterday. And when they were trying to work out the calculations at the end, I realized that a lot of them really did not understand at all what I lectured about. So I'm just going to kind of give you a heads up on that. We need to understand this slide in order to do the calculations for today's lab. So if there's something that I'm forgetting to tell you, or if something isn't clear, please say something. It'll save a lot of time later. So here we have a volumetric flask. This flask will hold 1 liter of water. And so what we're going to do is we're going to put our sodium chloride into this flask. We're trying to make a 1 molar solution. That would be 1 mole of sodium chloride in 1 liter of solution. So that's why we're using a 1 liter flask. We're going to put in 1 mole of sodium chloride. Well, you can't measure that on the balance, so you have to convert that to grams. You weigh out 58.44 grams of sodium chloride. So that's the amount of the solute. Put that in the flask. Then we're going to add DI water. We want the salt to completely dissolve before we fill it all the way up to the line. Because once the level of the liquid gets up here in the neck, it's very difficult to mix this thing. If you keep it down here, you can swirl it around and swish it around and mix it much easier. So we want to do that. We want to get all the salt dissolved. When the salt is dissolved, meaning it looks like water now, there's not floating things no matter how tiny, then you're going to add some more water. There's a mark on the neck, and that mark may be higher on some flasks than on others. It's put there specifically on that flask to measure a precise amount. So you're going to fill this, bless you, so that the bottom of the meniscus is right at that line. The last couple of drops, you probably do not want to use your wash bottle unless you're super good. I'm not good enough with a wash bottle because sometimes when I press really carefully, I get one drop, and sometimes I get a big squirt, right? If you go over the line, you really should just dump it out and start over again. Nobody wants to do that. So what do? Well, put some of that DI water in a small clean beaker and use your plastic transfer pipette. It's like a little eyedropper, right? And so you can very easily and in a controlled way add 1 to 3 drops of water so you can get it just right. Then you put a stopper in this. I'll show you how to hold it in lab. And to mix it thoroughly now, we have to invert it at least 10 times. Okay, any questions about that? So when we make a solution like this from the solid, the mass of the solid that we put into the flask is what we need to convert to moles. And the volume of the whole solution that we made is the volume that we use to calculate the molarity.
The lab documentation says measure 15 grams of NaCl,
Mm-hmm.
but then on there it says 58.4 grams.
Well, this is an example. It's not specifically for the lab, but that's a good question. And in the lab, it says to weigh out 15 grams. It just says 1.5, and then record the precise mass. And sometimes students will do the calculation just using 1.5. Well, what was the point in weighing it out then, right? It's not exactly 1.5. We're trying to get around 15, but we're actually measuring it because we want to know it more precisely. So let's do an example. We're calculating the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So it says calculate the molarity. So that tells me I'm going to need to use an equation. So molarity equals the moles of solute. Here the solute is sodium nitrate, divided by the liters of solution. We'll often abbreviate that SOL''N, solution. So I've got some numbers here. I've got a mass of sodium nitrate, and I've got a volume. The volume is given in liters, and that's the volume I need to divide by. So I can put that into the equation, 2.50 liters. But I need the moles of solute. So I have to calculate that. And calculating molar masses and converting between grams and moles is something that should be very straightforward for you at this point. Okay, we end up doing it a lot, just all the time. So 45.4 grams of sodium nitrate, I want to multiply by moles and divide by grams to get the number of moles. And the conversion factor here would be the molar mass, which I have to calculate. So there's 1 sodium, 22.99, and there's 1 nitrogen, 14.01, and 3 oxygens, 16.00. I'm getting 85. Does that mean it's exact? No, it just happened to be a whole number. Ever gone to the grocery store and the bill comes out to be $100 even? And you're like, ooh, maybe I should play the lottery today, right? I got lucky or something. It just happens. This still would have probably 4 significant figures, right? 2 decimal places. So 1 mole of that compound, 85.00 grams. Got the 45.4 divided by 85. 0.534. The sig figs on this number of moles are going to be limited by the 3 sig figs in the mass. So 3 sig figs, I'm going to use this number, so I definitely want to carry along 2 extra digits, and those are the moles. So that's the number I put in the numerator, 0.53411 moles. And then I divide by the 2.5. And my answer here should have 3 significant figures. The units be moles per liter. So when I round that, I'm going to get 214. And I can write moles per liter, or I can write capital M. Capital M stands for moles per liter. So this is 0.214 molar sodium nitrate. Any questions? Molarity is a really useful calculation, just like molar mass was very, very useful. We use it to convert between moles of solute and liters of solution. So instead of needing to use a balance, we can measure things out in a graduated cylinder or with a pipette or something and know how many moles of solute we have. So if we had a 0.500 molar sodium chloride solution, this tells me that there are 0.500 moles of sodium chloride for every liter of solution. And so we can write 2 different conversion factors. And this is how we convert between volume and moles. So let's calculate the mass of sucrose in this solution. We've got 1.55 liters of sucrose solution, and the concentration is 0.758 molar. So we've got 1.55 liters of solution. We've got 0.758 capital M. Now, in my experience, students tend to forget what the capital M means, and then they have trouble because it doesn't cancel out with anything. So instead of writing capital M, write what it means, moles divided by liters. And again, anytime you have something per something, make it a vertical fraction. Okay, so I've got liters and I've got moles per liter, and what am I trying to find? Grams. I'm trying to find grams of sucrose. And they gave me the formula because we don't expect you to remember that one. So I've got 2 numbers given to me, and sometimes we have a hard time deciding which one is the starting and which one is the conversion factor. The units will help you out here. This is moles per liter. That's the conversion factor. So I want to start with this volume of solution, and I have to figure out how to get to grams of the solute. This concentration allows me to convert between moles of solute and liters of solution. So I can go from liters of solution to moles of the sucrose. Can we convert from moles of that to grams? Sure we can. We've got the formula, we can calculate the molar mass. So I have 1.55 liters, and I'm going to go to moles. I'll be dividing by liters. And then from there I want to go to grams. And I'll be dividing by moles. So this one here, moles per liter, that's the concentration, the molarity. The 0.758 is with the unit mole. So here I'm multiplying 0.758 moles per liter. And then I need the molar mass of sucrose. So I have to calculate that. $342.296. I could round that, but it doesn't seem worth the mental effort. 342.296. The other numbers that I was given, and this is very typical of problems given to students. We've got 3 sig figs and 3 sig figs. And if we use at least 4 sig figs in our molar masses for the elements, we'll always have at least 4 in our molar mass here, and so that's not going to limit the number of sig figs. So 1.55 times 0.758 times 342.26.
Wouldn't the 1.55 limit your sig figs to 3?
It is limited to 3. These are limiting my final answer to 3. This always is going to have 4 or more, and so we don't even need to worry about it. I did something wrong in my calculation. I left out a 9 in there. That's no good. 96. I'm getting 402.16. And that would be grams of sugar. And so I can round that to 402. Any questions? Yeah.
So how we know when is the kilogram instead of gram?
Well, here it's asking how many grams. So then you should give the answer in grams and not kilograms. If it asks for kilograms, then you need to say kilograms. Is that what you're asking?
Yeah. So like if I don't have anything like that,
If it just says what's the mass, then you technically could give it in any mass units.
so even grams.
Yeah. Yeah. But if it specifically says how many grams or how many kilograms, then you really need to give the answer with that unit. Okay? We often store solutions in a more concentrated form, just like they sell the orange juice in concentrated form. It takes up less space, for one thing. These solutions are called stock solutions, and we keep them in the stock room. We have them in stock, so we can use them whenever we want to. So we'll take those stock solutions and we'll dilute them, and unlike the orange juice where you want to have it always end up the same concentration, we can dilute these to whatever concentrations we need. When you dilute a solution, you do not change the amount of solute. You're just changing the volume. So if we think about the orange juice, right? So you've got that can, you can picture it, the can of frozen orange juice concentrate. There's a certain amount of orange goodness in the can, right? When I dump it into the pitcher, now it's in the pitcher. If I add water, does that change the amount of orange goodness in the pitcher? No, it's still the same amount of stuff, right? But the volume's gotten bigger because I added water to it. I diluted it. The concentration is less, but the volume is greater. The concentrations and volumes of solutions are related by this equation, M1V1 equals M2V2. So the molarity of the first solution times its volume. Well, molarity has units of moles per liter, and if the volume is in liters, then that gives me the moles of solute, right? And over here, the molarity of the second solution times the volume of the second solution, moles per liter times liters, that also gives me the moles of solute. This equation works because when you add more solvent, you're not changing the amount of solute. So whether that explanation meant anything to you or not, M1V1 equals M2V2. So here's an example of diluting a solution. We're going to do this in lab today too. So in this example, we're taking 0.150 liters of a 10 molar stock solution. So pouring that into this flask. 10 moles per liter times 0.150 liters, 1.5 moles of the solute. Okay? Then we're going to add water to this. Okay, if I fail to add water to this, is the concentration going to change? No, I just put it in another container. We're going to take the stock solution that we make by adding some sodium chloride solid to water, and we're going to take some of that and we're going to dilute it. So we measure out a particular amount. We're going to use a pipette instead of a cylinder. You put it in here. To dilute it then, you have to add the water, right? Otherwise, with the orange juice, you've just got this sloppy, thick concentrate stuff that won't be yuck, right? You have to add the water to make it right. So we've got our concentrated part in here, and then we add more water. Again, we fill very carefully to line up the meniscus with the line, cap it, invert it at least 10 times to make sure it's thoroughly mixed. Okay, so then this is now less concentration. Here we're being told this is a 3-liter flask. So we have 3 liters of volume. The concentration now is 0.5 moles per liter. We still have 1.50 moles of solute. As the volume gets bigger, the concentration goes down. So let's see how we would do a calculation with this. To what volume in milliliters should you dilute 100.0 milliliters of a 5 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? Now, I'll warn you, students really like this M1V1 equals M2V2 equation, and then they try to use it in all sorts of inappropriate places. So you can only use it when you're diluting something. So in this example, we've got this word dilute. That tells me I can use this equation. The other clue is I've got a calcium chloride solution to start with and a calcium chloride solution to end up with. Students try to use this when they're doing stoichiometry. It doesn't work. It's not right. Sometimes you get the right answer, but it's just a coincidence, okay? So only use it when you're diluting a solution, not when there's a chemical reaction. So here we're diluting a solution, and so we've got M1V1 equals M2V2. I've got a bunch of numbers. I'm going to write those down and label them. So I've got 100.0 milliliters. I've got 5.00 capital M. Okay, let's write what that actually means. 5.00 moles divided by liters. And then I've got 0.750 capital M, which is 0.750 moles divided by liters. I can tell from the units which of these are volumes and which are molarities. Right, these two on the bottom, that's a molarity, a concentration, and that's a molarity, moles per liter. This one, milliliters, is a volume, so I'm going to call that one V. The way the equation is presented I like because it's just got ones and twos. It's not saying concentrated or dilute. It doesn't matter which solution you call one or which you call two. You just have to get things paired up correctly. 100 milliliters of 5 molar. These two numbers go together. So I'm going to call those 1. I'm going to call that solution 1. I have 100 milliliters of 5 molar. Those two go together. This concentration is the concentration of the other solution. And we're wanting to know what volume of the second solution. So I've got my equation up here, and I'm going to rearrange this and solve for V2. So I'll divide both sides by M2. Because M2 over M2 is 1, it cancels out. Got V2 is equal to M1 V1 over M2. Make sure that you're copying the 1s and 2s correctly. I've got my numbers all labeled so I can put them in the equation, and I definitely want to include my units. So M1 is 5.00 moles over liters. And volume 1 is 100.00 milliliters. Molarity 2 is 0.750 moles over liters. Now this milliliter here isn't going to cancel the liter there. But maybe it's not going to be a problem, because let's look at what's happening with the units. Here I've got moles per liter in the numerator and moles per liter in the denominator. Those, both the moles and the liters, are going to cancel each other out. The moles cancel, the liters cancel, and I'm left with milliliters, which is really nice because that's what they're asking for. They want the volume in milliliters. So with this dilution equation, sometimes you have to convert to liters, but sometimes you don't. So just stick all the units in there and see what happens with them. So I've got 5 times 100 divided by 0.75, and I'm getting a lot of 6s. 666.66 repeating. And the unit would be milliliters. Wow, that's a ridiculous number of 6s. I've got 3 sig figs, 5 sig figs, and 3 sig figs. So my answer should have 3 significant figures. So that would be right there. I'm going to keep the underlined digit and look at the next one to see, do I round up or down? I round up, and I get 667 milliliters. So if I take 100 milliliters of this more concentrated solution, I'm going to end up with a larger volume of the less concentrated solution. Any questions? Molarity is useful when we're doing stoichiometry problems, because a lot of our reactions occur in solution, and so we can measure volumes and know the concentrations of our reactants and products and do stoichiometry calculations. So this is a variation on grams to moles to moles to grams. So instead of grams to moles, we may do volume. And at the end, instead of grams of your product, you might end up with a volume of product. Grams to moles to grams is still a good place to start, and then just adjust it as needed. Let's do an example. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? Just like with the other stoichiometry problems, let's use this balanced chemical equation to organize the information. So here I've got a concentration, 0.150 capital M. Well, that refers to the HNO3, and so I'm going to write that number here. Yeah, it helps to write the correct number. Instead of capital M, I'm going to write moles over liters. And then I've got another number, 35.7 milliliters of Na2CO3. So 35.7 milliliters of that. And it's also giving me a concentration. Moles per liter. So overall, plan for stoichiometry, grams to moles to moles to grams.
You can't use M1V1 because there's no dilution.
Right. We do not want to use M1V1 equals M2V2 here because we've got two different compounds. And so that tells me I'm not just diluting a solution. I am changing one thing into another. And the reason that we shouldn't use dilution there is because the dilution equation does not take into account the stoichiometry. I get 2 moles, I use 2 moles of this for every 1 mole of that. What's really sneaky about that dilution equation, if the stoichiometry is 1-to-1, you'll get the right answer. But the stoichiometry is often not 1-to-1. So only use it when you're diluting. What are we trying to find here? Volume in milliliters of the HNO3. So our path, grams to moles to grams, we're not going to be doing grams at the end, right? We want milliliters. And our starting is also going to be milliliters. Now, do you see a potential issue with the units? I've got volumes in milliliters, but my concentrations are moles per liter. This happens a lot. There's 2 things you can do. You can take this volume in milliliters and convert it to liters, and then do the calculation. You'll end up with a volume in liters, and then you have to convert that back to milliliters. The other thing we can do is kind of a trick, but it's entirely valid, and I was not thinking ahead quite enough. So I've got moles per liter. When I have a fraction like that, if I do the same thing to the top and the bottom, do I change the value of the number? No. So we could take a fraction and multiply by 2/2. That's the same as multiplying by 1, right? What if I take this fraction and multiply by milli over milli? 1,000 over 1,000. Might seem like kind of a random thing to do, but then I would get millimoles over milliliters. Now, when I combine this with milliliters there, the milliliters are going to cancel out. So that'd be cool, huh?
So you don't have to do the milliliters.
So I don't have to go milliliters to liters. I don't tell the 3A students about this. They can't handle it. But you guys are in 1A, right? You don't have to do this, but I just want to show it to you because I think it's kind of cool. So over here where we've got moles per liter, I'm going to move that over and just make a little space. 0.150 moles per liter is the same as 0.150 millimoles per milliliter, right? And then I'm going to end up with milliliters down here. So what I'm doing in my path is instead of moles, I'm going to do millimoles. And I need to do this one too. So milliliters to millimoles to millimoles to milliliters. Yes?
If you don't want to do millimoles, can you just do, like, I guess the normal way where you convert to liters and then back to milliliters?
Yes, absolutely. And really, which method is easier for you depends on how your brain works. Okay, so some people really like this method. Other people are very comfortable converting milliliters to liters without actually getting out a calculator or doing math or anything. I can do that because I've practiced it a lot. This in liters is 0.0357 liters. You're just moving the decimal point 3 places. The trick is you have to move it the correct direction, right? And some people tend to do it the wrong way. So then that doesn't work so well. So let's go ahead and try this with the millimoles. So millimoles to, start over. Milliliters to millimoles to millimoles to milliliters. It just doesn't have the same ring to it. Okay, 35.7 milliliters of Na2CO3. And next will be millimoles of Na2CO3. And I'll have milliliters in the denominator. So those will cancel. And then I'll go to millimoles of HNO3, and I'll have millimoles of Na2CO3 in the denominator. And then here I'm going to have milliliters and millimoles HNO3. So the first one is the molarity of the sodium carbonate solution. So 0.108 moles per liter or millimoles per milliliter. The last one is the concentration of the HNO3. Millimoles are on the bottom, so the number goes on the bottom, 150, and milliliters on top. Usually in the middle we had moles to moles, here we got millimoles to millimoles. The ratio is the same. It's the coefficients from the equation. There's a 1 in front of sodium carbonate and a 2 in front of HNO3. So 35.7 times 0.108 times 2 divided by 0.150. This is what my calculator says. And my concentrations and my initial volume all had 3 significant figures. So this answer will be rounded 51.4, yes, I don't need that, milliliters of the nitric acid. Any questions? Yes?
You named it a millimole, but you never actually moved the decimal point.
I did not move the decimal point. You are correct. Because I put milli on top and on the bottom. So if I move the decimal point, then the milli would go away and I would have different numbers. The ratio would be the same. So here, I moved the decimal point and made this into liters. If I'm going to do that, then I'm not going to use millimoles here. So
So the trick was just basically renaming it?
Basically renaming it, yeah. So I'm taking that unit moles per liter and I'm multiplying the top and the bottom by the same amount so it cancels out. Right, exactly. So some of you will go, oh, that's cool. And some of you will go, what the heck are you talking about? Okay, so this blue part is for the latter group. So if all of that was just confusing to you, convert to liters. And now we're going to go liters to moles to moles to liters. So we'll end up with 0.108 moles of the sodium carbonate per liter. The liters cancel. And here we've got 2 moles of HNO3 to 1 mole of the guy with too many letters and numbers in his name. And then here we've got liters of HNO3 divided by moles of HNO3. And so then if I just stop here, I end up with 0.0514 liters. And I have to convert that back to milliliters because the question specifically says we want the answer in milliliters. So you move the decimal point 3 places, 51.4 milliliters. We're starting the same place, we're getting to the same answer, but how you get there is partially up to you. You can't fly to the moon with your space jetpack because that doesn't exist, right? But you can walk this way around the block or that way around the block. Any questions?